What's up, everybody? Pastic here, and we are continuing to talk about calculus and limits. And here we're going to discuss the limit-based definition of continuity. And what we're going to find out is that there are three parts to the limit-based definition of continuity. And it's going to be mucho importante to be using this three-part definition whenever you're asked to determine whether a function is continuous. Most likely, this is the three-part definition that you will have to provide as evidence to show that a function is indeed continuous. So, without further ado, we are on page 57 on the notes, and it says, for the function graph below, fill in the table with the given information. After filling in the table write the three pieces of information that must be true in order for a function g of x to be continuous at x equals a. So we're looking at continuity at a single point. So let's scroll down and let's start filling out the table here. So what we got so far is it says the function, is it defined? If so, what is its value? So that should be pretty straightforward. Let's do that first. So at x equals -6, it looks like the function is not defined. So I'm going to say no. At x equals -3, it looks like it is defined and the value is 2. At x equals 0, looks like the value is -1. At x equals 2, looks like we've got a vertical asymptote, so we're going to go with a no. X equals 6, defined, and looks like the value is 1. And x equals 8, defined, and it looks like the value is -4. Okay, so let's fill out some more of this table. What is the value of the limit as x approaches a from the left of each one of these? So as x approaches -6 from the left, we are going to trace the function like that, and it looks like the limit is 5. Let's keep on going across on this one. So x approaches 6 from the right. Looks like, again, the limit is 5. And what is the limit as x approaches a of g of x? I would say that appears to be 5. Is the function continuous at x equals -6? We said it's undefined, but the limit exists. Is it continuous? Well, you're looking at a hole at -6. And a hole, by definition, is called a point or removable discontinuity. So the answer is no. X equals -3, what's the limit as we approach -3 from the left? Approaching -3 from the left, it looks like our limit is 2. Approaching -3 from the right, it looks like our limit is -4. What is the limit of g of x as x approaches -3? Well, there is none, so I'm going to write D and E. And then the last one, is it continuous at -3? I think pretty clearly no, and the type of discontinuity is a jump discontinuity. When one part of the graph ends there and another part of the graph ends in a totally different location, that's called a jump discontinuity. So again, no continuity here. How about 0? At 0, what's the limit as we approach from the left? It looks like it's -1. What is it as we approach from the right? It looks like it is, again, -1. What about the limit in general, the two-sided limit? It looks like it, again, is -1. Is this function continuous at 0? It appears to be. How do I know that? There's no discontinuities. There's no point discontinuity. There's no jump discontinuity. There's no asymptotic discontinuity. The curve at x equals 0 is smooth and indeed continuous. X equals 2. X equals 2. Let's see. We have a vertical asymptote. Limit as we approach from the left does not exist, but we're going to put positive infinity. Limit as we approach from the right does not exist, and we're going to put negative infinity. For the full two-sided limit, we are certainly going to put does not exist. And is the function continuous at +2? The answer is no. And we have an asymptotic discontinuity. For 6, we've got limit as we approach from the left is being 4. Limit as we approach from the right appears to be -2. And the two-sided limit does not exist, and the reason it does not exist is because these two values don't equal. Same thing here. That's why we're going to say it does not exist. And then the last one, is it continuous? No, we've got again a jump discontinuity at positive 6. Last one, -4 is the defined value at 8. So at 8 we are here. So the defined value. Limit as we approach from the left appears to be -2. Limit as we approach from the right, oh, I just screwed that up. As we approach from the left, it is +4, and as we approach from the right, it is -2. So let me fix that. All right, so as we approach from the left, it's +4, I do believe. No, I'm screwing this up again. Hold on. All right, trying this again. I think I kept on looking at 6 instead of 8. So as we approach from the left, approaching x equals 8 from the left, the limit is indeed -2. Same thing from the right, also -2. We've got a hole there. And then what's the two-sided limit? It is indeed -2. Is the function continuous there? No. Why? Because we have this guy right here. We have a hole. We have a point discontinuity. So now we got to ask ourselves, what does it take for this graph to be continuous? We don't want to look here. 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 It looks like there's only one spot where this function is continuous out of the selected values that we chose. So let's look at this one row and let's see if we can work backwards to determine our three-part definition of limit-based continuity. First thing right here. The function is defined and it has a value that is real. So that's what we're going to say. So f of a is defined and it equals a real number. So I'm going to add f of a equals L, where L is some real number. That's the first part. The second part, I'm going to jump to this right here. And what that part is showing me is that the left-handed limit is equal to the right-handed limit. So left-handed limit is -1, right-handed limit is -1, and that is a good thing because that means that the two-sided limit exists. So what does that tell me? That tells me that, and I don't have a lot of room to write this here, so we might run out of some space, but that tells me this: the limit as x approaches a from the right of, we call this f of x. This is g of x. Let's fix that. All right, all fixed. Of g of x equals the limit as x approaches a from the left of g of x. And they both equal some real number L. That also tells us that the two-sided limit exists. So limit as x approaches a in general of g of x equals L. Not only does it exist, but it equals that same letter L. And then the last part is to tie all those pieces together. So we look back down here. Not only does the limit exist, but it's also equal to the value of the function at a. So yes, the limit on the left exists. Yes, the limit at the right exists. Yes, the two-sided limit exists, but it's also the same as the value of the function at that specific location. So that's the last part. So now we will formally state that the limit as x approaches a of g of x is equal to the value of the function at that specified location. So this slide here, this page here, is going to end up being very important. It is the three-part definition of limit-based continuity. This right here is our three-part definition of limit-based continuity. We're going to need to use this, cite it, and use it to find all kinds of different stuff throughout this unit and as we move forward in calculus. I will catch y'all next time. Thanks for sticking with me. Take it easy, y'all.